Cathode rays. J.J. Thomson, 1856 to 1940. He constructed a cathode ray tube. This consists of a partially evacuated glass tube. So there's a little bit of gas inside, but not as much pressure as the outside. And you pass a current through this, and you get a beam of particles. They're called cathode rays. They travel from the cathode to the anode. That's why they call them cathode rays, because they come out of the cathode. The cathode is the negatively charged electrode. So you can, here's a picture. Hopefully there's like a beam of light here, and those are the particles going from the cathode to the anode. So he investigated the properties of the particles in that cathode ray. He found that they travel in a straight line. They are independent of the composition of the material from which they originate. So that metal cathode that they come from, you can use different metals, and the cathode rays are exactly the same. It doesn't matter what you make the cathode out of. And those particles also carry a negative electrical charge. Electrical charge is a fundamental property that some particles have. Here's just a very brief review of the properties of electrical charge. Opposite charges attract each other. If you have a positive and a negative charge, they're going to be attracted to each other. If you have two positive charges, they will be repelled. If you have two negative charges, they will also be repelled. Electrical charge behaves in many ways just like magnetic charges or magnetic fields. And you've all probably played with magnets, right? Even just sticking stuff on the fridge. This is kind of cool how it just sticks to itself, right? Opposites attract, like charges repel. Anybody had Brio trains when they were little? Or little siblings? Little wooden trains, and they hook together with magnets. Very cool. If you turn the car around so that the magnets are backwards, they will repel each other. You cannot get it to stick together. You can push them together, but as soon as you let go, they push each other apart. That's like the like charges repelling each other. So the particles in this cathode ray have electrical charge. He was able to measure the charge to mass ratio of these cathode ray particles by deflecting them. They have a charge, and so if you put an electric field on them, you can bend them. So this is an example of this here. We're making cathode ray particles here and shooting them through. When we apply either a magnetic or an electric field here, you can cause the particles, the beam, to move. And you can control how you move it. And this is really the basis of the technology in a cathode ray television, a CRT television, the old tube kind. It had a cathode ray beam that rastered back and forth and gave you your picture. So he was able to measure the ratio of charge to mass. And that value was minus 1.76 times 10 to the third coulombs per gram. Okay, so very nice. You don't need to know that number, but there it is. This implied that the cathode ray particle was about 2,000 times lighter than hydrogen. Hydrogen, the lightest known atom at the time, and still the lightest known atom. So we've got a particle that's 2,000 times smaller than the smallest atom. This was incredible. There is something smaller than an atom. So this then gives us problems with the idea that an atom is indestructible, because here we just made particles that are smaller than atoms. So what's up with this? Thomson had discovered the electron. Electrons are small, negatively charged particles, very low mass, and they are present within all atoms. So this was the first evidence that all elements are actually composed from the same particles. All atoms contain electrons. Millikan's oil drop experiment. So here, American physicist Robert Millikan performed an experiment which allowed him to deduce the charge of a single electron. I'll show you a video in just a minute, but let's talk through this real quick. So here he has an atomizer and some oil. And so he can spray a very fine mist of oil into this chamber. Little teeny tiny droplets. Not unlike a perfume atomizer that'll take that liquid and make a mist out of it. Those particles, of course, are subject to gravity and they will begin to fall. Here we have a positively charged plate, and there's a little tiny hole. And these particles, some of them are going to fall through the hole. Down here, we have a negatively charged plate, and we have ionizing radiation that is traveling across. When that hits oil droplets, some of them will become charged, positive or negative. They'll become charged. And then there's a light source so that they could look through this microscope and actually watch the particles. So let's show the video. And for my YouTube followers, this video is also in the playlist. So by watching these charged particles and adjusting the charge, the positive charge on this plate, positive charge will attract a negative charge, right? So if we make this positively charged plate strong enough, it'll keep the negative particles from falling. If we reduce this, then they'll continue to fall. If we increase this too much, we can actually get the particles to rise up. And so they would adjust this until they would just be suspended. Knowing the mass of the particle, the acceleration of gravity, and the electric field, they could calculate the charge on each drop. And of course, each drop had a different charge. Some of them had a +2, some 2 electrons, some, -2. Some had maybe 3 electrons on them. But if you looked at them, they were all multiples of one number. And that was the fundamental charge on the electron. So that's this number. That is the fundamental charge of a single electron. So this kind of talks about the experiment a little bit. What I liked about that video is it also had the text right in there, and so if you want to, you can watch it again and again and get the details. So having that number and using Thomson's mass to charge ratio, we could get the mass of a single electron. I think I was supposed to put, I don't know what I was supposed to do with this slide. That happens sometimes. But you take the charge from the oil drop experiment, and you take the mass to charge ratio from Thomson's cathode ray experiment. The charges cancel out, and you get the mass of the electron.